Heavenly Father, thank you for this class and thank you for this day and thank you for your amazing grace for the presentation last night. And you do really amazing things. You surprise us with just amazing things. And I thank you for that. I pray your blessing on this class right here today. You know who we are, what we need, and what would be important for us to understand of this class and what goes on. And I pray you just ferret out the stuff, blow away the chaff and the stuff that's genuine, that you would just help us to remember it and help it to grow. In Jesus' name, amen. Okay. So, for those of you that weren't here on Friday, I will put the notes on Friday up. You've got a handout that I handed out Friday. So you got that and you can go through the notes and pick out the ones that you need to cover. The stuff last night, the choir singing, I have been to probably between 50 and 60 of those things. I've been here 31 years. I've been to one here every year, and then they used to have us go to Mount Carmel's every year. So that's 2 every year, 2 Easter programs and 2 Christmas programs. I've been programmed enough for 20 people, or maybe 60 people. Anyway, but I really got something out of this last one. It was really, it was ministry to me, which is really cool. I mean, I thought it was cool. So, anyway, aside from that. So, we're picking up on this sun rays thing. And we got through, we get this through this far? People that were here?
The sun rays?
No, this
We didn't
is,
even get to this.
this is days.
Okay,
Yeah, we not got to this yet.
okay.
This is starting day.
So we're just starting right there. Good. And then Friday, there is not a class. Let me just, my own sense. Okay. Study day is Friday. So that's fine business. I just wanted to check that when it was fresh in my mind. Okay, so Engel and Sons rays. So we've talked about this actually in an earlier lecture, but I'm reinforcing it. I'll pass about your tests I'll give hopefully some time at the end of this class to go and pass out your tests. From experience, the next test, which will be your final, and I'll talk to you about when we do that, when I get a list of when we're supposed to, and when I'll give you usually a flexible time, so you don't have more than, and you don't have just an hour to take. Of course, most won't take that long. But it's probably gonna be the most difficult of the tests that I give. Just we're covering stuff, this weather business, there's some stuff that is counterintuitive. It's just not, it's not like, okay, this and this and this. So if you struggle on this test, then the only thing I know to do is encourage you to take a little more time to prepare. Because the last one typically delivers the lowest scores of the tests that I have given, as far as in my memory, just because of this weather stuff. Some of it's pretty easy, and a lot of it blends together, but anyway, so I'm just saying. So 3 causes for seasons. Cover this: revolution, the tilt, and the parallelism of the Earth's axis. So going around, the areas near the equator do not experience dramatic changes in daylight for those of you who have lived close to the equator, you'll find that. When I was in Kenya, where I was staying with a farm family, it was really close to the equator. And man, when night hit, it was sudden. Like, it was daylight and then it wasn't anymore. It wasn't so gradual like we have here anyway, the gradual descension into it. But anyway, so they don't experience dramatic changes in the daylight periods or angle of sunlight. I mean, the sun goes from 23.5 degrees south to 20.5 degrees north, and so, but it stays, it's overhead twice every year in the equator, and so the angle doesn't change that much, and they don't have seasons so much as we do here. The angle at which the sunlight strikes the earth affects the temperature, not the distance from the sun. So the likelihood that you'll get a question talking about the distance from the sun, does that affect the temperature? No, it doesn't. It doesn't. It's the angle at which the sunlight strikes the earth. That's what affects the temperature. Like this little diagram here. And some of you on this last one, so the angle of the sun's rays strike, when it's more overhead, they strike a smaller area. The same amount of radiated energy strikes a smaller area when it's more directly overhead than when it's not. It not only comes at a stronger angle, but it comes through more atmosphere, like this. This is less atmosphere, this is more atmosphere, so a larger area, it's then, the intensity is decreased. So, when the sun is more directly overhead, it covers a smaller area, more intense, less intense when it's more at a greater angle. And it covers a lot, so the same amount of radiant energy strikes, but it strikes it over a larger area, and that makes it.
Just tapped on the.
Cord, I think. Yeah. See, there you go. There you go.
Yo.
So since light disperses and kind of like fades out as it goes further away from the source, why would the sun's distance not affect the temperature?
It doesn't as you're further away than the source. This is at a different angle. In fact, this can be closer to the earth than this, but the distance that it's closer is a very small amount. We're talking about 94.5 million miles to 91.5. So we're talking about, I think they say it's about 3% difference. Very small, not enough to make a difference. Even though it's farther away in one sense and closer in another, it's not enough distance to make a significant difference. In 93 million miles, that's the average distance. But this says it doesn't matter if this was closer, if it was on the closer thing, what I think it is, it's closer here, but the angle, it cuts through more atmosphere, so there's more opportunity for the radiant energy to be scattered or absorbed, so it doesn't reach the earth. And then when it's coming at an angle like this, it has the same amount of radiant energy coming out of here, but it has to cover a larger area. And as it gets farther away, as it spreads out, it gets weaker as it spreads out. That,
Yeah.
that's, thank you. I appreciate questions. Because if you have them, the likelihood is somebody else is having them too, but they're just thinking, okay, well, I'll figure this out later, maybe. I've done that a lot. As the distance of sunlight travels through the atmosphere increases, the more sunlight is absorbed and reflected before it reaches the Earth's surface. And here's an illustration of that right here. When it's more directly, right here, overhead, smaller area, when it cuts through this much more distance than this, So it travels through more atmosphere, and there is, as I was saying, more atmosphere for the radiant energy to be diffused, scattered, absorbed. Okay. The sun's rays striking the earth. Places on or near the equator get nearly vertical rays from the sun all through the year, not directly, but nearly 23.5 degrees. It's pretty consistent. Thus, they are relatively hot climates. Temperature variation, hottest at noon? No, afternoon. Just because noon, it's more directly overhead, but what it does, after several hours after noon, the lower air receives more heat from the sun and the ground than it loses. So, the sun comes in, it heats the ground, that re-radiates. And it happens to re-radiate at longer wavelengths. So we'll talk about that when we get to the greenhouse, the business of greenhouse. Well, let me just, so when the sun's light comes into a greenhouse, you know what a greenhouse is? A glass encased room that you grow plants in. So the wavelengths come in from the sun through the glass. They hit the plants, they hit the ground, they hit the floor, they hit stuff in there. And it cools them. And then it's re-radiated back. Well, the shorter wavelengths don't get out of the glass as well as the longer wavelengths. So they get trapped in there. So that's why it heats. You got shorter wavelengths coming through the glass, and then it hits colder objects, and then it re-radiates it back. Well, it radiates at longer wavelengths. It's changed the temperature of that stuff, so they're longer, and some of that stuff can't get out the glass. So it keeps in there, and that's the same thing with the earth. It hits the earth, and then it re-radiates at longer wavelengths. So some of it gets taken by the atmosphere that it didn't get taken going in, because they were shorter wavelengths going in. But this is, when's the hottest? Is it noon? No, it's afternoon, because it's heated. It not only is coming in at the radiant energy is coming into the earth, but it's also being heated when it strikes the earth and re-radiated. So you've got that. And just like the coldest hour usually comes just before sunrise. Because the lower air is losing heat all through the night. And so it's losing heat until you get the sun up that is starting to generate heat. Clear days usually have the widest range of temperatures. Why? Because they're heated more easily and also cool more quickly. And with no clouds to absorb heat and no clouds to hold heat in, and when they don't keep it in, they keep it from radiating into space. June 21st is the time of the strongest sunlight in the northern hemisphere. It's as far north as the sun will get, 23.5 degrees. Northern latitude, that's June 21st. But is that the time of the highest temperature? No, not usually. July and August are typically the hottest. Know a pond or a body of water in your home area, July and August will find it the warmest and not mid-June. because water warms up more slowly and cools off more slowly. That's why in the summer, when you get, or in the fall, so the sun has been heating this particular, let's say eastern Kentucky, during the summer, and then you get a cold snap, not freezing, it's just a drop in temperature. Well, when you drive out and you look at the North Fork, you'll see steam rising off the water. Well, that's because cold air can hold as much moisture as warm air can. So when you got a lot of moisture, when you got a lot of heat, the air can hold, we'll cover that as well, but it'll hold a lot more moisture. When it cools, it can't hold as much, so it condenses. And that's just, when that cool air comes, it tends to do that. In fact, it does it both directions, both when in the fall and in the spring, you'll see that. Yep.
What did you say about the coldest days, the degree of angle?
The coldest days,
Um,
or you mean this year?
so June 21st is at 23.5 degrees.
Yeah, now that's when the sun, in the northern hemisphere, that's where the sun gets to be directly over. But that's as more straight as up as it gets at 23.5 degrees. But that's not the warmest. It's the strongest sunlight, but it's not the warmest, because the sun has been warming up all these other areas and they continue to generate radiant energy. So it's July and August, well, here, anywhere where I live, July and August are the hottest. And where I live, where I grew up, there's a lot of water. And so you could find the same place on the East Coast or on the East, same latitude, completely different temperature structure. So we'll talk about that as we move forward in this too. So, and so if you got an area with a lot of water, that it takes longer to heat up, but it lasts longer. So you've got that heated body. It doesn't penetrate that deeply, but it penetrates a lot more deeply than it does on Earth. Well, right here, okay. The sun's rays penetrate deeper in water, several meters, versus the top few centimeters in soil. So when you have sunlight on a body of water, it penetrates deeper, so it can warm more. Now it spreads out more, but it can warm that. It takes longer to warm up, but once it gets warm, it stays that way longer. And with soil, it doesn't. Soil is reflected, and it depends you see where over in the far left, those waves are kind of, well, let's say they're rolling. So then you get a little, it's a little different. When they're more choppy, the light is more diffused. But with reflected light, it doesn't penetrate very, very deeply into the so where it's just level, where there's no waves or anything, it penetrates a little deeper. But it's scattered as blue light. That's why when you see, that's why some water is so beautifully blue in Hawaii. That is how it is. Just incredible. So water spreads heat more easily because it's fluid. And some solar energy is used in the procedure of evaporation, so less energy is available to heat up the water. So we'll get into evaporation. That's a large part of what generates hurricanes and those kind of things that come into the water, but I'm just make you aware of this. But we will talk about that a little more in detail. So, surface response to sunlight. So this is looking at the surface of the ground. The color, the dark absorbs better than the light. So a dark surface like the asphalt here absorbs better than a white surface. If you have the dark surface and white surface, the white would reflect, the dark would more absorb, so the dark surface would heat up more than the light surface. Rough surface has more surface area than smooth. So this is just an illustration. You have a flat surface, and that is flat right here. So all the sunlight hits this evenly. Well, this if you've got a rough surface, then that sunlight is taken in all that rough area. So that has more area. And then dry increases quicker than wet. So dry versus wet, and then snow and ice reflect. So they reflect sunlight, so they continue to be cold. So dark absorbs better than light. Smooth. Rough has more surface area, so that would absorb more light. And then dry increases quicker than wet. And you're gonna have to know these different mechanisms of heat transfer. There's 3 of them: radiation, conduction, and convection. So this is obviously a pot of water or some liquid, and you've got an electric stove that's heated. So this gives off radiant energy, it's radiation. So it heats what's next to it. And as this heats it, the hot rises. You can see that it rises, it gets to the top, it cools, it goes back down and rises again. This is convection. This is what we talked about when we talked about volcano or within the earth. You have convection of molten material. And then conduction, this is where, because of this action of heating, this handle is hot. If you've ever taken a hold of a handle that looked cold, but it just didn't have any, yep.
So does induction fall under the conduction category? Because like with an induction cooktop or like a
Like an induction oven?
yeah,
No, that's convection oven.
they don't like with those particular types of cooking surfaces, you just put the pan on and the pan just gets hot. The surface doesn't actually get hot. I don't know exactly how it works.
What?
That's kind of crazy. I'm not kidding.
Okay, I've got a ceramic top stove, but it's got elements underneath it.
And also,
So,
I don't know. They also make induction heaters for when you're doing blacksmithing.
yeah,
You don't have to make contact directly with anything hot. It just makes whatever material hot.
I'm thinking that it would fall under something would be generating the heat. And either the heat would be transferred in a material like this. The heat is transferred, so it's conducted into this handle. It's conducted, or it's radiant energy radiating here that heats this, that heats both the pot and conduction through the handle, but it also heats what's in here, which then results in convection. So,
Oh, it's magnets. Never mind, just forget my question.
okay,
That puts it under conduction.
it's okay.
Stupid magnets.
Magnets are really interesting. The vast majority of energy coming to and leaving the earth is in the radiation form. Radiation form. So not conduction, not being transferred to something, and not convection, it's radiant energy radiating out from. Conduction is a transfer of heat through matter by molecular activity. That's why that handle got hot, because it's conducting the heat from below. The pan is heating, which transfers it to the handle, and that's conduction. The energy of molecules transferred through collisions, one molecule to the other, with heat flowing from the higher to the lower temperature. So heat goes from higher to lower. Air pressure goes from the higher to lower. Just like in a plane, we talked about that a lot. Well, some of you were here about the hole in the plane, and all of a sudden the pressure tries to equalize. So it's a lot lower pressure outside the plane, inside the plane it's higher, so it tries to equalize. That's why I have those little masks that pop down for you, if you're in that condition. Conduction, for the most part, is important only between the Earth's surface and the air directly in contact with the surface. So the lower level of air, that's what you get. As a means of heat transfer for the atmosphere as a whole, conduction is the least significant. So conduction is the least significant, radiation is the most significant. Conduction is the least, radiant energy is the most. Heat gained by the lower layer of the atmosphere from radiation or conduction was most often transferred by convection. Convection is a transfer of heat by the movement of a mass or a substance from one place to another. Like in that case, the case of a pot, the liquid is contained, so it's a transfer of liquid, but you can do the same with air. In fact, well, I think I said this at the beginning of class. So if you had a stove right in the center of that room, right in the center of this room, you had a stove. So you get that stove, you start putting heat to it. Well, the heat is going to draw the cold air in. It's going to heat the cold air to be warm air. And the warm air is going to rise. And it's going to hit the ceiling, which is cool. And so it's going to heat the ceiling, and it's going to spread out along the ceiling, down the walls, and then back drawn. So you get convection of the air. You're not seeing it, but you can feel it, at least initially, that you get convection. As the air is heated, it goes up, it hits a cool surface, it cools and falls back down because it's heavier, and then it's drawn back in to be heated again and goes up. That's the principle. Okay. Convection, remember, can take place only in some liquid or gas. And the air is gas, so it can take place in gas, like the air, or it can take place in liquids, In most situations involving heat transfer, conduction, and convection, radiation, it occurs simultaneously. Radiation. The sun emits light and heat as well as the rays which give us a suntan. Although these forms of energy comprise a major portion of the total energy that radiates from the sun, they are only a part of the large array of energy called radiation or electromagnetic radiation. All radiation, X-rays, radio waves, heat waves, light waves, is capable of transmitting energy through the vacuum of space at 186,000 miles per second, and only slightly slower through our atmosphere. So, it comes through our atmosphere, it's a little slower than that, but not much. So we've had this is just a repeat of what we talked about earlier. Radiation requires no material to transmit it. All objects, at whatever temperature, emit radiant energy. You and I do. We are emitting it even now. There are detection gadgets that can detect heat, radiant heat from bodies or anything. So they can, that's why they can, you can be out in the woods crouching down and something can fly over and look for radiant heat and they can know where you are. They may not see your face, but they can know that there's radiant heat energy, and they can tell by temperature gradations where it's coming from. You can run, but you can't hide. Hotter objects radiate more total energy per unit than colder objects, and the hotter the radiating body, the shorter the wavelength. Well, we've covered that earlier when we talked about stars. They're hotter, more energy. The sun's heat emits on the green wavelength. It emits everything but radio waves to gamma rays, but predominantly, the dominant measure is between the wavelength that is the green area. The sun emits that. We don't see that because things are scattered, but for example, very hot metal rod will emit visible radiation, producing a white glow. Upon cooling, they'll emit more of the energy at longer wavelengths, like red. Eventually, no light will be given off, but if you place your hand near the rod, the still longer infrared radiation will be detectable as heat. So if you've done that, if you've fooled with a forge, and you can get it white hot, and then it cools to red and you can see it, but when there's no visible color, you can get your hand, and if it's a big piece of steel, you don't have to get your hand very close to that thing to feel the heat. If you grabbed it, you'd be severely burned. Okay, so, and note, objects that are good absorbers of radiation are good emitters as well. So if it absorbs well, it emits well as well. Gases are selective absorbers. So this is objects that are good absorbers, are good emitters. Gases are selective in absorption and radiation. Thus the atmosphere, which is nearly transparent, does not absorb certain wavelengths of radiation, is nearly opaque to others. So, like the ozone layer, we talked about that before, the ozone layer picks up shorter wave radiant energy coming from the sun and coming from cosmic rays. The shorter wave ozone layer, it has some of the molecules there absorb that energy so it doesn't get to us. It doesn't absorb everything. There's some of the rays that go right through, they don't bother. They just wave as it passes, but some of it absorbs. So that's why the ozone layer tends to be hotter or can heat up, because it's absorbing that energy which generates heat. Okay, so incoming radiant energy. Now your book may have a different design, I think, than this, but they basically say the same thing. Some about 30%, this is incoming radiant energy. So radiant energy is coming from the sun, and about 30% or 31%, I mean it's about, of the solar energy reaching the outer atmosphere is reflected back into space. So in this diagram, that says that here's this radiant energy coming in, 30% of it doesn't get in, it hits something here, it's some of the upper atmosphere, it hits some molecules and is reflected, just kicked right back into space. So we get 70% that's still coming in. 20% is absorbed by atmosphere and clouds. So 20%, you got the ozone layer, you got other things, and clouds that absorb another 20%. So basically, at the bottom, you've got 50% that is going to get through. 30% kicked back into space, 20% is absorbed before it gets to the Earth. So you've got 50 units of solar radiation. If you talk about units, 50 units gets to the Earth, gets down to the Earth. And once it gets to the Earth, then something happens. Out of this 50 units that gets to the Earth, 7 units, it's conducted within the atmosphere. 23 units, I don't know how they figured this, but we'll just trust them, is lost by evaporation. So it hits and it's evaporated, which results in condensation in clouds eventually it will. And 20 units by long wavelength radiation. So it comes in short waves, and then it cools and it goes back longer waves, and some of these long waves are also absorbed by our atmosphere. And 12 of this 20, 8 is like this, 12 units long wave radiation in which the atmosphere is transparent. So it goes back through the atmosphere. The wavelengths, I guess the stressing of wavelengths, because they are, some things absorb certain wavelengths and some things don't. Some long wavelengths may be just the right wavelength to avoid some of the atmosphere coming in and also be able to get out of there. That's what that 12 units is. So that's a rough, you can look in your book, it has a description that you can look over to see where that stuff goes, or how it goes. This is general. It does it differently. This isn't for every place on the earth. There are some places that it penetrates more. In Arizona, you probably get a different scene than you would, or in Texas, in the wide open spaces where there are less cloud-covered days. Yep.
So in the city, I know it's more hot, would the concrete make the sun, radiate,
Yes.
reflect?
Amen. That's exactly right. I think now flying, so when you're flying and you look down, and it's a sunny day, very few clouds, and every once in a while you see a cloud. You see a cloud hanging there. And I'm not sure, I think I've asked somebody, but I don't remember. Because when you get a wide, like a parking area, like a shopping mall, let's say somewhere in Kansas, you have a big shopping mall. And it's got a black surface tarmac. It's just a big black surface. Well, that's gonna heat up faster than the cornfields that are all around it. So it heats up faster, so that causes heat to rise. And when heat to rise, it depends on what levels it rises to, but you can get clouds from that rising heat that you wouldn't get from the cornfields around it. And I don't know if those are what generate those, just singular clouds. I mean, you have a cloudless sky, and then you have this cloud there. And I've wondered when I've flown why that would be, and I think that is it. That it would generate, the temperature would rise, and as it rises, if it gets up so high, then it would begin to condense, because there are condensation levels where the air is cool enough to not be able to hold a certain amount of moisture, and then you get condensation, so you tend to get a cloud. But you wouldn't get a cloud it wouldn't be enough to get the whole mass of clouds. So, a fraction of total radiation encountered is reflected by a surface. It's called albedo. So for the Earth, it's about 30%. That's what's reflected. It varies from place to place considerably, depending on the amount of cloud cover, particulate matter in the air, as well as the angle of the sun's ray and the nature of the surface. So you have all these variables that would have an effect on the amount of total radiation reflected by the surface. So gases are selective absorbers, meaning that would be something you should put a star or asterisk by that, because I know you're gonna get at least one question about that. Gases are selective absorbers, meaning they absorb strongly some wavelengths, moderately in others, and only slightly in still others. So, just because they absorb one wavelength doesn't mean that they'll absorb in every wavelength the same. They won't do that. Gases are selective. When a gas molecule absorbs light waves, the energy is transferred into molecular motion, which is detectable as a rise in temperature. Remember, molecular motion is what defines the temperature. Nitrogen is a poor absorber of all types of radiation. Oxygen and ozone are efficient absorbers of ultraviolet radiation. So that, and there's a span of ultraviolet rays. There's some that are longer than others. Remember that the ultraviolet, the James Webb Telescope is looking at infrared, which is at the other end of the spectrum. But there's a wide range of infrared radiation, just as there's a wide range of ultraviolet. And within the ultraviolet, you can have a span of wavelengths within that, what we call ultraviolet. And some of them would be absorbed and some of it wouldn't be. Just because it's ultraviolet doesn't mean the oxygen and ozone would take care of all of it. They would care of some of it. Oxygen removes most of the shorter ultraviolet wavelength, high in the atmosphere. And ozone observes the longer wavelength ultraviolet rays. But not all of it. You've got some that observes just, if you look at the, I don't remember what page it is, but when you look at the wavelengths and you look at visible light, if you could expand the visible light, you'll see that ultraviolet, which isn't visible, it's on the other end of it, covers a wide range. You have shorter wavelengths or shorter and longer. And so the closer it is to the visible, it's longer, and then it goes toward gamma or toward X-rays and gamma or X-rays, and it gets shorter and shorter. So you got a range in there, and the oxygen absorbs some of it, the ozone absorbs others, different wavelengths. To me, that just seems so interesting that when God said, let there be light, and I believe that he was creating that whole electromagnetic spectrum of all those wavelengths that would have so many different uses and capacities, and he created an atmosphere for this earth that would take care of the harmful ones for the people living here. But it's science. I don't know who said it, I didn't create it, and I probably botch it when I'm gonna tell you. But science examining God's creation is just amazing how he did what he did and covered all the different things that had to be covered for it to be efficient. Water is another one. Water itself, we spend whole semester talking about the water. The only other significant absorber of incoming solar radiation, other than oxygen and ozone, so 1 and 2, is water vapor. And those three account for most of the solar radiation we get that is absorbed in our atmosphere. So when you talk about absorbing things, it's oxygen, it's ozone, and it's water vapor. So let me see. Are we done? Let me see where we are on this thing.
Just beginning,
Are we half?
first page front.
We
We still got
just
more to
do-
go.
Just one?
Only halfway through the
More
first
like
page.
Halfway through the first page.
Mm-hmm.
Okay. Let me finish this, sir. I'll give you your test pages and if you'll bring them to me on Wednesday. I'd like them back, but I'll let you look at them. So I'll pass them out right after class. So, for the atmosphere as a whole, none of the gases are effective absorbers from radiation with wavelengths between 300 and 700 nanometers. So none of what's out there is effective between that range. This region of the spectrum corresponds to the visible range. This explains why most visible radiation reaches the ground and why we say that the atmosphere is transparent to incoming solar radiation. And most of the sun's radiant energy is in that range, that green range is 500 to 520 or 530 nanometers. So that's what most of the energy the sun is generated, but it also extends to either side, but that is the visible range. Atmosphere does not require the bulk of its energy directly from the sun, but rather radiate radiation. So that's important, you should put an asterisk by that. The atmosphere does not acquire the bulk of its energy directly from the sun, but from re-radiation. Energy that has hit the earth or some object on the earth and then is re-radiated from the earth's surface. This is of the utmost importance to the dynamics of the weather machine. This very thing, that the re-radiation is of the utmost importance to the dynamics of the weather machine. Approximately 50% of the solar energy that strikes the top of the atmosphere reaches the Earth's surface, directly or indirectly, and is absorbed. Most of the energy is then re-radiated skyward. Since the Earth has much lower surface temperature than the sun, terrestrial radiation, which is coming from the Earth, is emitted in longer wavelengths, just as I was saying. It comes in from the sun, it touches anything that's cooler, and it changes its wavelength. So it comes in at one wavelength, it hits something cooler, and it's generated then in another wavelength. The bulk of terrestrial radiation has wavelengths within the infrared range, so you don't see it. And the infrared is longer wavelengths than red. You've got red is the shortest visible wavelength, and then you've got infrared, and that's where the bulk of the radiation that is after it hits the Earth, its terrestrial radiation is then of the longer. The atmosphere as a whole is a rather efficient absorber of radiation at the infrared range, terrestrial radiation, which means that most of the re-radiation is kept close to home. Water vapor and carbon dioxide are principal absorbing gases in that range. And we've got a lot of water vapor here. Evaporation from oceans, from rivers, from creeks, from brooks, from creeks, from all those things. So we get a lot of, that's why this atmosphere, all atmosphere, tends to be warm. Water vapor absorbs roughly 5 times more terrestrial radiation than do all the other gases combined, and accounts for the warm temperature found in the lower troposphere, where it's most highly concentrated. Because the atmosphere is quite transparent to the shorter wavelengths, solar radiation, and more to shorter wavelength solar radiation, and more readily absorbs the longer wavelength terrestrial radiation, the atmosphere is heated from the ground up rather than vice versa, okay? Because the atmosphere is transparent to shorter wavelengths. What does that mean? That means shorter wavelengths can come zooming in. It's transparent. It doesn't interfere with them. They just come on in. But it absorbs the longer wavelength, and that's what happens. It hits the Earth, it's changed to a longer wavelength, and that is what they more readily absorb. So, the atmosphere, our atmosphere, is heated from the ground up rather than from the sun down. Sun shines, radiant energy, it's re-radiated, that's what is, the atmosphere is heated from the ground up. This explains the general drop in temperature with increasing altitude experienced in the troposphere. The farther from the radiator, the colder it becomes. Okay. So, greenhouse effect. The greenhouse, that'd be pretty sweet.
That would be nice.
Oh, I'd like to live in that place.
That'd be a good place to take a nap.
Well, you would be. That wouldn't be a bad time either.